Hi everyone. Since this week it's an online week, I just thought I should record this lecture. This week we're going to start partial derivatives. Okay. Partial derivatives. First, we need to understand what is the partial function, because we're going to find the derivative of the partial functions. Partial function, it's a function of at least two independent variables. For example, let's say z is a function. It's a function of x and y. So for example, let's say this function of x and y is 2x squared plus y squared. You see here, y is no longer a function, it's independent variable. The dependent variable is z. Z is a function now of x and y. So don't confuse with ordinal functions. For example, you used to say, you used to think of y as a function of x in ordinal functions. So y is a function of x, maybe for example, it's x squared plus y. No, what I'm doing now. Maybe it's x squared plus 2. You see, this is the ordinal function of one variable. Y in this case was a function of x. Now, in partial functions, we use y as independent variable as x. So in this case, z is a function of two variables. It can be a function of more than two variables, but for example, this is a function of two variables. It's a partial function. So we're going to find a derivative of such functions. Okay, but before I go in details with this, let me motivate this chapter by looking at the volume of a cylinder. You know, a volume of a cylinder is given by pi r squared h. You see, this volume is a function of two variables, r and h. So in real life, we have a function of more than one variable. For example, v is a function of r and h. This is a volume of a cylinder with a radius r and height, which is h. Okay, let me draw a cylinder here. I'm motivating a partial derivative here. So let's consider this cylinder. This is a cylinder, right? With a radius of r, sorry. And the height h. Okay. If we look at this cylinder, what's happening when we increase the radius of the cylinder? What's happening to a volume? You see, the volume will change if we increase the radius. Okay, the volume will increase if we increase the radius, but let's keep h constant. Let's keep the height of this cylinder constant. But if we increase a radius, the volume of a cylinder will increase. That's why we consider the derivative of a volume with respect to r, while h is a constant. Okay, because you know the derivative is a change in V over change in R. There will be a change in volume with respect to R. That's why we consider the derivative of a volume with respect to R. So this derivative in notation, we use this symbol. This is a partial derivative sign. It means this is a derivative of V. If we're deriving the partial function, we use this symbol instead of D. So this means a derivative of V with respect to R. So this means it's a partial derivative of V with respect to R while we keep other variable constant. You see we keep H as constant. So this is the same symbol as this one. It means we derive your function with respect to R, but if we write it like this, it means we're deriving the partial function, but while we keep other function as constant. Okay? So let's find the derivative of V with respect to R while we leave H as constant. Let's go back to the volume of a cylinder. Volume of a cylinder, we said, is given by pi r squared times H. So what will be the partial derivative of V with respect to R? So this is a constant, and pi also is a constant, it's a number, right? So we're just gonna go straight and deriving R, because we're deriving V with respect to R. So the answer will be, okay, let's leave the constant here, pi h, let's deriving R, it will be 2R. So the partial derivative of V with respect to R while we treat H as a constant is going to be pi times H times 2R when we're deriving R squared there. So this will be 2 pi HR. So this is a partial derivative of a volume with respect to R. Okay. Now let's go back to this picture of a cylinder. Now, if we keep R as constant, now we increase a height. You see there will be a change in volume. Okay. So again, we can consider a change in volume with respect to H while we treat R as a constant, because there will be a change in volume that is caused by a height. Okay, so now we can also consider the derivative of a volume with respect to H. Okay, now while we treat R as a constant, so just to give a definition here, we want to find the derivative of V with respect to H while we keep R a constant. R doesn't change, but there will be a change in volume that will be caused by a height. So again, in partial notation, this is a partial derivative of V with respect to H. This means we treat other variable as constant. In this case, the other variable will be R. It will be a constant. So this partial derivative of V with respect to H, so let's deriving V with respect to H. So we're gonna treat this as a constant. Now let's deriving H. So when we're deriving this with respect to H, it will be pi r squared times 1. So the answer is just pi r squared there. Okay. So let me rewrite this. So let's say if you have a function, let's say v, a volume, is pi r squared times h. If you have two variables, there will be two partial derivatives. The first one, because this is a function of r and h. So the first derivative, which is a partial derivative of v with respect to the first variable, which is r, we found that we're deriving r while we treat h as a constant. So this, we found that is 2 pi rh. Okay, we're just deriving r squared. Okay, and also the partial derivative of v with respect to h will be pi r squared, because we derive with respect to h while we treat r as a constant. Okay. Okay. You know, from ordinary derivatives, let's go back to the function of one variable. For example, if you have a function of 2x squared, so when you're finding the derivative here, you leave the constant there and then you go straight to the derivative, to the function that you're deriving. So that's why it's 2x, that's why you're getting 4x when you're deriving this function, because we go straight to this function and derive it. We leave the constant like this. That's why we leave our constant eceleni when we're deriving that variable. Don't be confused by this. So we're not going to limit ourselves with a volume. So any function of at least two variables, you just follow the same step. I'm going to do the example here. Example 2. Let's say a function u is given by x squared plus xy plus y squared. And the question say find a partial derivative of u with respect to x and a partial derivative of u with respect to y. Okay. So a solution, you see u is a function of x and y in this case. So that's why we deriving this using partial derivative, because it's a function of two variables. So the partial derivative of u with respect to x is going to be, so we're deriving x. So the first term is going to be 2x plus, in the second term, we're deriving x. So it's going, a derivative of x is 1 times y, it's y. And the derivative of the third term, remember, we're deriving with respect to x while we treat y as a constant. So if constant is alone on a term, so the derivative of a constant is 0, right? So the answer here is 2x plus y. Okay. Now let's find the partial derivative of u with respect to y. So now we're going to derive this function with respect to y. So the first term is going to be 0 because x is a constant and we treat x as a constant. So the derivative of the first term is 0. So it's going to be 0 plus the derivative of the second term. Remember, you're deriving y now, eh? So go straight and deriving y. So here is going to be x. And then the third term is going to be 2y because we're deriving y, eh? So the answer is just x plus 2y. Okay, these are two partial derivatives of these functions. If a function have two variables, you will have two partial derivatives. If you have a function of three variables, it will be, you'll have three partial derivatives. Okay. Let me give you more examples here. Okay. All right. Example 3. If z is equal to 2x minus y times x plus 3y. You see z is a function of two variables. You want to find a partial derivative of z with respect to x and a partial derivative of z with respect to y. Okay, this is the question. You're given a function, it's a function of two variables, and then you want to find a partial derivative of two variables. Okay. Solution. To find the partial derivative of z with respect to x, you see you have a product of two functions here. When you derive a product of two functions, you know you're applying a product rule, right? But remember, you're deriving your function with respect to x. But since we're deriving the product of two functions, we're applying the product rule. So the product rule say we're deriving the first function while we leave the second function, plus we leave the first function and multiply by the derivative of the second function. Yeah? So let's follow the product rule because we're deriving the product of two functions, yeah? But it's a partial fraction. So let's derive the first function, but with respect to x, we are applying the product rule. Derivative of the first function with respect to x. So when we're deriving the first function with respect to x, it's going to be 2. While we leave the second function, x plus 3y. And then plus, we leave the first function, which is 2x minus y, multiplied by the derivative of the second function with respect to x. When we're deriving a partial derivative with respect to x, we concentrate on x. So the derivative of this is going to be 1, derivative of x. So the next step is just simplification. This is going to be 2x when we multiply x inside, plus 6y plus 2x minus y. So this will be 2x plus 2x is 4x, and 6y minus y is 5y. Okay, so this is the first derivative with respect to x. Now let's find the derivative of z with respect to y. Partial derivative now of z with respect to y is going to be, again, we derive the product of two functions. So we apply the product rule, but now we derive with respect to y. So the product rule say derive the first function, but with respect to y, it's going to be minus 1. When we derive the first function with respect to y. While we leave the second function, which is x plus 3y, And then plus, now we leave the first function, which is 2x minus y, and derive the second function. The derivative of the second function with respect to y is going to be 3 here. Okay, this is your derivative, and the next step is just simplification. Let's simplify this. So let's multiply -1 inside the bracket. It's minus x minus 3y, and here let's multiply 3 inside, plus 6x minus 3y. Yeah? So this will give us minus x plus 6y, minus x plus 6x is 5x. And minus 3y is minus 6y. Okay. All right. Let me give you this exercise. Try it on your own, and then you can ask me in class if you're still stuck. Why this is not going up now? Try this exercise. If z is equal to 2x minus y over x plus y, find a partial derivative of z with respect to x and a partial derivative of z with respect to y. Take this question, and then if you stuck or you have a problem, please ask me in class. But just to give you a hint, this is a partial function, right? So you want to derive a function over a function, so you're going to apply the quotient rule. And remember, when you're finding the partial derivative of z with x, so you're going to concentrate your derivative with respect to x while you treat y as a constant. Okay. Let me give you more example again. I think this is example 4, I guess. If z is equal to sine of 3x plus 2y, find partial derivative of z with respect to x and a partial derivative of z with respect to y. Okay, you see z is a function of two variables, sine of 3x plus 2y, x and y. So let's find the partial derivative of z with respect to x. So we're deriving sine of a function. So when you're deriving sine of a function, it's going to be cos of a function multiplied by the derivative of the inner function. So, but we focus our derivative with respect to x. Okay, let's derive this sine of a function. It's going to be cos of a function, my inner function is 3x plus 2y multiplied by the derivative of the inner function. So the derivative of the inner function, but with respect to x, is going to be 3. The derivative of the first term is 3. Second term is a constant because we treat y as a constant there. So the answer here is just 3 cos of 3x plus 2y. Is it like that? Now let's find the partial derivative of z with respect to y. So from our function here, this is our function. We derive it with respect to y now. Again, we're deriving sine of a function. It's going to be cos of a function 3x plus 2y times a derivative of the inner function, but with respect to y. So it's going to be 2, because the first term is a constant, x is a constant. So derivative of a constant is 0 plus derivative of 2y is 2. So yeah, this is the derivative. And we can simplify this and say this is just 2 cos of 3x plus 2y. Okay. All right. You understand with the first partial derivative, So now let's go and look at the second derivatives of partial derivatives. So we call it second partial derivatives, but I will illustrate the second partial derivative with this example. Example 5. Consider z equal to 3x squared plus 4xy minus 5y squared. So this is my function, but it's a function of two variables again, x and y. We're going to find the first partial derivative, which is the first derivative, and then the second derivative, which we call them a second partial derivatives. Okay, first let's find the first partial derivative. There are two first partial derivatives because we have two variables. The first partial derivative is going to be with respect to x. So the derivative with respect to x here is 6x. We're deriving the first term with respect to x. And then the second term with respect to x, deriving x is going to be 4y. 4y. And then this term with respect to x, we treat y as a constant, so this would be 0. So this is the first partial derivative with respect to x. There's another first partial derivative with respect to y. So when we derive this function with respect to y, the first term is 0. The derivative of the first term is 0 because x is a constant. And the derivative of the second term is 4x. And the derivative of the third term is minus 10y. We derive with respect to y. So these are first partial derivative. You see this first partial derivative, each partial derivative is a function of x and y again. So the first partial derivative with respect to x is a function of x and y. And also the first partial derivative with respect to y is a function of x and y. So again, we can find a second partial derivative on each partial derivative. So we can consider a partial derivative with respect to x in the first partial derivative. That's how we write. So we can derive the first partial derivative with respect to x with respect to x. Okay, because it's a function of two variables. And then we can also consider a derivative with respect to y in the first partial derivative with respect to x. But let's first derive this with respect to x. So we're going to derive this with respect to x. But before we do that, let's look at this notation. So this is a second partial derivative because we're finding the second derivative from the first partial derivative. So in notation, this is same as second partial derivative. We write like this over x squared. So if you see this, it means you're deriving the second partial derivative from the first partial derivative with x, if you have x squared here. So you're deriving a function with respect to x twice. You see, we find the first partial derivative with respect to x, but in the first partial derivative, again, we derive with respect to x. So that's why we say we use this notation. It's the same as ordinary derivative. Remember, a function of first derivative, a function of one variable. When we're finding the second derivative, let's say with respect to x, we find from the first derivative. This is the same notation, d squared y over dx squared. You remember this. This is a notation for a second derivative from the ordinary derivatives, like a derivative of one variable. This, you know, this is a second derivative notation. So it's same, but here is different. Is this symbol? The different is this symbol. Okay. Yeah. So let's find this second partial derivative. Let me remove this because it will look messy. All right. So the second partial derivative of z with respect to x. So this means we're deriving this function with respect to x, the first derivative, so it's going to be 6. And also we can consider a second derivative with respect to y in this derivative with respect to x. So this will be, we're deriving this first derivative with respect to x. So in notation, this would be a second partial derivative of z with respect to y in a first partial derivative with respect to x. So the order is very important. So this means we're finding the derivative with respect to y in the first partial derivative with respect to x. So the derivative that is being performed, that is going to be performed now, is this one, y. So we start by, when you're finding this second partial derivative, you first need to find the first partial derivative with respect to x, and then find the second partial derivative from the first partial derivative with respect to x. So this will be, we're finding this second derivative with respect to y in the first derivative with respect to x, which is this one. So, but we derive with respect to y, yeah? So it's going to be 4, yeah? And we just derived this function, the first derivative, because there's also a partial, we derive with respect to x and with respect to y, yeah? And then just remember the notation, yeah? Okay. And again, there is a first partial derivative with respect to y. Again, it's a function of two variables x and y. We can find a partial derivative, a second partial derivative with respect to x in the first derivative with respect to y. Yeah? Okay, now you understand the rule. So let's derive this function with respect to x. Yeah? So the answer here is going to be 4. When we derive with respect to x, the derivative that is being performed now is this one. With respect to x, we find it from the first derivative with respect to y. And then again, we can derive this function, the first derivative, find the second derivative with respect to y. If it's y squared, it means you're going to derive your function z twice with respect to y, as we did here with respect to x. So, but here, if we derive with respect to y, it's going to be minus 10. These are the answers. Okay, and then you're done. So, this is a function of two variables. If you have two variables, you're going to have two first partial derivative, right? You know that. If you have two variables, you're going to have 4 second partial derivative. Okay. If your function is of a two variable, you have 2 first partial derivative and 4 second partial derivative. Let's say if this function is a function of 3 variable, you're gonna have 3 first partial derivative and then 6 second partial derivative. Okay. Again, what you notice here, you see this second partial derivative are equal. They both equal to 4. Yeah? So this tells you ukuthi a second partial derivative of z when you're deriving a y in the first derivative with respect to x is going to be equal to the second partial derivative of x when we derive from y. Okay, so these are always going to be equal. Normal to a surface value, you're always going to find this equal. Okay, so when you're finding this second, you can start with any variable, it's up to you. Okay, let me do another example here. All right. I think this will be example 6. If z is equal to x cos y minus y cos x. Okay. Find first and second partial derivatives of a function z of z. If z is equal to x cos y minus y cos x, find the first and second partial derivatives of z. Okay, solution. Let's first find the first partial derivative. Since this is a function of two variables, you're gonna have two first partial derivatives. The first partial derivative is of z with respect to x. So let's derive this function with respect to x. So we're going to treat y as a constant, which means cos of y is a constant there. So let's focus on deriving x. So it's going to be cos y minus, let's derive this with respect to x. We go straight in deriving x. So we return y. So when you're deriving cos x, it's going to be sine. Okay. So we're deriving this function z with respect to x. The first term when you're deriving x is going to be cos y. The second term when you're deriving x, we're gonna return y, and deriving cos x is going to be minus sine x. Minus sine x, and this negative will make this positive. So this is the first partial derivative, but with respect to x. And then let's find another first partial derivative with respect to y now. Let's derive this function with respect to y. The first term, we're just going to ignore x because it's a constant and go straight and deriving cos y. It's going to be minus sine y. Minus sine y. And derive this with respect to y. So you just derive y. It's going to be minus cos x. So these are the first partial derivative. So the second partial derivative, they're going to be 4. Because you'll get 2 from the first partial derivative with respect to x, and another 2 will get them from the first partial derivative with respect to y. So let's find now the second partial derivative of z with respect to x. So we find this. It means we're deriving z twice with respect to x. So we're finding from the first partial derivative with respect to x, the second derivative. So, but we derive with respect to x. So there's no x in the first term, so we're going to treat this as a constant. So the derivative is 0. And when we derive this with respect to x, we're going to ignore y and just deriving sine x. Derivative of sine x is cos x. Okay. And now this was a derivative with respect to x from the first partial derivative with respect to x. And now let's find the second partial derivative now with respect to y from the first partial derivative with respect to x. So let's derive this function with respect to y. the first term have y, so it's minus sine y plus sine x, because we're deriving y, yeah? We're deriving y. Again, let's derive this with respective to maybe y first. So this would be a derivative of y twice. So when we're deriving y here, this would be we're deriving y, so we're going to ignore a constant x, so it's minus x cos of y. When we're deriving y, there's no y here, so this would be a zero derivative of the constant. And again, a second partial derivative of z. Now we're deriving x from the partial derivative with respect to y here. So we're going to deriving x. So when we're deriving x, you get minus sine y, and derivative of this would be minus cos x. So the derivative of cos x is minus sine. So we can make this positive. So plus sine x. Okay. All right. What you notice here, you see this second partial derivative is equal to this second partial derivative. You see it's always the case. This second partial derivative with respect to y from the first partial derivative with respect to x will be a second partial derivative with respect to x from the first partial derivative with respect to y. So yeah, always. So yeah, you're welcome to find one second partial derivative and conclude another second partial derivative is also equal to this. Yeah. All right. Let me stop here for now. But let me give you exercise again. Try it. I'll do this from the next lecture. If v is equal to ln of x squared plus y squared, prove that a second partial derivative of v with respect to x plus a second partial derivative of v with respect to y is equal to 0. If v is this function, it's ln of x squared plus y squared. And again, you see v is a function of two variables, x and y, so that's why we have partial derivatives. So prove this identity. So take the left-hand side and show is equal to right-hand side there. So find these partial derivatives and then add them and show they equal to 0. Okay, thank you so much. This is a lecture for Monday. For tomorrow, which is Tuesday, I'll do the recording this afternoon. Thank you so much.